Hey, what's going on, everyone? And welcome back to the channel. If you're new here, don't forget to give the video a thumbs up and subscribe, comment, let me know what you do or don't like about the videos I'm making. Today's the second day in a row I'm recording a video, and we're going to see how long we can keep this mother jammer going. So in keeping with the theme of talking about things that I just have a lot to say about, I want to talk to you today about the foundational paper for the generative pre-trained transformer, which is the particular style of neural network that's used. It was used in the creation of ChatGPT and other generative AI tools. So it's, it's a pretty grabbing title. Attention is all you need. So we're not going to read the entire thing word for word, but we will read the abstract word for word. So the dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. So what they're saying here in the first sentence is that at the time that this paper was written, the most prevalent and talked about in the machine learning community transduction models are based on complex recurrent or convolutional neural networks. These are just other types of neural networks, just like GPT. The best performing models also connect the encoder and decoder through an attention mechanism. This attention mechanism is what this paper is really about, right? Hence the title, Attention is All You Need. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrency and convolutions entirely. Experiments on two machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Our model achieves 28.4 BLEU on the WMT 2014 English to German translation task. Okay, so this is like a standard way of scoring performance for a machine learning model. This will be a well-known data set. Improving over the existing best results, including ensembles, by over 2 units of measurement. Our model establishes the new single model state-of-the-art score of after training for 3.5 days on 8 GPUs, a small fraction of the training costs of the best models from the literature. And this is significant. Okay, I want to point this out. This is significant. This is why you can run llamas or models like Llama on your own computers, is because transformers are very efficient. They're very, very efficient because the people who wrote this paper, they really discovered something interesting. They really discovered the value of self-attention to a machine learning process. So they go on to say, we show that the transformer generalizes well to other tasks by applying it successfully to English constituency, parsing both constituency, I'm leaving this in, parsing both large and limited training data. Okay, here's some notes about the testing. Work was performed at Google Brain, Google Research. Okay. Now we get into the introduction. Recurrent neural networks, long short-term memory, and gated recurrent neural networks in particular have been firmly established as state-of-the-art approaches in sequence modeling and transduction problems such as language modeling and machine translation. Numerous efforts have since continued to push the boundaries of recurrent language models and encoder-decoder architectures. Okay, so what are they saying here, right? They're saying, they're saying we all in the community, the machine learning community, know and take it as a fact that recurrent neural networks and long short-term memory and gated recurrent neural networks have been firmly established as, an interesting technology in our space, right? So this is just like well-known information at the time. Recurrent models typically factor computation along the symbol positions of the input and output sequences. So they're saying there is a human decided input and output sequence, and it's being judged on that, I think is what they're saying. In a typical recurrent neural network task is that like this input and output are established by humans. Aligning the positions to steps in computation time, they generate a sequence of hidden states as functions of the previous hidden state and the input for position t. This inherently sequential nature precludes parallelization within training examples, which becomes critical at longer sequence lengths, as memory constraints limit batching across examples. Recent work has achieved significant improvements in computational efficiency through factorization tricks and conditional computation. While there's also improving model performance in the case of the latter, the fundamental constraint of sequential computation, however, remains. So what they're saying is it's difficult for us to do these tasks in parallel for one reason or another. I don't know why that would have been the case at this time. Attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing modeling of dependencies without regard to their distance in the input and output sequences. In all but a few cases, however, such attention mechanisms are used in conjunction with a recurrent network. So what they're saying is you have this old architecture that you have set up from, 2016, back in the ancient days, and you've stapled a new piece onto it, but you're still using the existing architecture. In this work, we propose the transformer, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state of the art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. So what they're saying here is like, we came up with a new architecture, newer than a 2016 architecture, now in 2017, talking years here, architecture that will make it way cheaper to train your models. So what's the background of this? The goal of reducing sequential computation also forms the foundations of extended neural GPU, ByteNet, and conv-S2S, all of which use convolutional neural networks as basic building blocks, computing hidden representations in parallel for all input and output positions. These models, the number of operations required to relate signals from two arbitrary input. In these models, the number of operations required to relate signals from two arbitrary input and output positions grows in the distance between positions, linearly for conv-S2S and logarithmically for ByteNet. This makes it more difficult to learn the dependencies between distant positions in the transformer. This is reduced to a constant number of operations, albeit at the cost of reduced effective resolution due to averaging attention-weighted positions, an effect we counteract with multi-head attention as described in section 3.2. So what they're saying is in your convolutional neural network, you do a bad job of getting things that are not, I believe what they're saying is that the decisions that the model is making are ordered in kind of a sequential way where it's like you won't have anything that's drastically better than the other thing. They're all going to be about the same because of this averaging process that they're talking about. And they're saying if you use multi-head attention, you can pull more interesting insights out of the noise when the resolution of the neural network changes. Self-attention, sometimes called intra-attention, is an attention mechanism relating to the different positions of a single sequence in order to compute representation of the sequence. Self-attention has been used successfully in a variety of tasks, including reading comprehension, abstractive summarization, textual entailment, and learning task-independent sentence representations. End-to-end memory networks are based on a recurrent attention mechanism instead of a sequence-aligned recurrence and have been shown to perform well on simple language question answering and language modeling tasks. To the best of our knowledge, however, the transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without sequence-aligned recurrent neural networks or convolution. In the following sections, we will describe the transformer, motivate self-attention, and discuss its advantages over models such as these examples. Most competitive neural sequence transduction models have an encoder-decoder structure. Here, the encoder maps an input sequence of symbol representation to a sequence of continuous representations Z. Given Z, the decoder then generates an output sequence of symbols of an element in time. At each step, the model is auto-regressive, consuming the previously generated symbols as an additional input to generating the next. So what they're saying is this attention mechanism is taking the last piece of content in addition to the piece that it's creating. And so it's basically making a stub. What they're describing here with their model architecture is the mechanism that they've created to give the model awareness of its previous input and the input that it's generating. So at all times, the model is aware of what was created or like which decision was picked and then on to the next decision. Okay, so it's just the awareness of the previous decisions in the chain. Here's what that architecture actually looks like sketched out. Okay, this is the actual architectural map. And the important things to pay attention to here are the inputs and the outputs, right? So you have the input embedding that goes through positional encoding and then is sent to both the feed forward, but first the attention. So here is where the last piece is created. Here is where the current piece is created. That information gets sent back up to another attention mechanism because attention is all you need, right? So now it's aware of the one that's being created, the one that was just created, the one that was just created before that, and so on and so forth, right? So the model is giving itself awareness of what past decisions it made to inform what decisions it will make next. And then it outputs, its confidence that it's got the right answer. And then, in the example of ChatGPT, that would be the next word that's being put down by the chatbot. So the transformer follows this overall architecture using stacked self-attention and point-wise fully connected layers for both the encoder and decoder, shown in the left and right halves of figure 1 respectively. So again, look at how similar this is. This almost looks like they're just moving memory, right? And at the end of the day, that's basically what they're doing. It's just in a really complicated, resource-heavy fashion. So, encoder and decoder stacks. The encoder is comprised of stack in this case, 6 identical layers. Each layer has 2 sublayers. The first is the multi-head self-attention mechanism, and the second is a simple, position-wise, fully connected and feed-forward network. We employ a residual connection around each of the 2 sublayers. Okay, so when they talk about the residual connection, they're talking about keeping the context, right? The model knows its own context, not only the decision it's making now, but also the last one that it made. Followed by a layer normalization, that is the output of each sublayer is layer norm, some math, is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimensions d by model equals 512. Okay, so they're just saying, this is the resolution of their model, right? The decoder is also comprised of stack in this case, 6 identical layers in addition to the 2 sublayers. Each encoder, the decoder inserts a 3rd sublayer, which performs multi-head attention over the output of the encoder stack. Okay, so multi-head attention, right? There's self-attention, now we have multi-head attention. Similar to the encoder, we employ residual connections around each of the sublayers, followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. So this multi-head attention is basically their way of keeping the context straight and not having like the model make different investments in the decisions it's making, right? The multi-head attention lets them unify the output of the model without bringing it down to an average. 2. Attention. An attention function can be described as mapping a query and a set of key value pairs to an output, where the query, keys, values, and output are all vectors. The output is computed as a weighted sum. So here's the example that they had before. And what they've done with H here in their diagram is they're showing concurrency. Like this is where they've built in their ability to parallelize their workflows. And it's because of the ways that they have their inputs coming in linearly into their attention mechanisms, and then they have it put out to the multi-head attention mechanism. So on the left, this kind of attention. On the right, our kind of attention, showing parallelism of the values where weight is assigned to each value is computed by compatibility function of the query with the corresponding key. Okay, so they say, of the values where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. We call our particular attention scaled dot product attention. This input consists of queries with keys and dimensions. The value of this dimension, we compute the dot products of the query with all keys divided by the square root of the outcome, and apply a softmax function to obtain the weights of the values. In practice, we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The keys and values are also packed together in matrices K and V. We compute the matrix of outputs as attention KQV equals softmax of this formula, or this, whatever, I suppose this whole thing is the formula. The two most commonly used attention functions are additive attention and the dot product multiplicative attention. Dot product attention is identical to our algorithm except for the scaling factor of 1 over the square root of the outcome. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer. While the two are similar in theoretical complexity, dot productivity attention is much faster and much more space efficient in practice, since it can be implemented using a highly optimized matrix multiplication code. So what they're saying is, the only difference in this mechanism that we're using and your mechanism that you used to use is that ours builds all of its data into a matrix that can be easily eaten up by computers, right? Because if you make something a matrix, it's easier to parallelize. And that intuitively makes sense to me. But if you have a better way of explaining it, make sure to leave a comment. And don't forget to like and subscribe and do all that fun stuff. So they get into multi-head attention. Instead of performing a single attention function with the D model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values H times with different learned linear projections to D through D whatever dimensions respectively. On each of these projected versions of the queries, keys, and values, we then perform the attention function in parallel, yielding D dimensional. output values. These are concatenated and once again projected, resulting in the final values as depicted in figure 2. Multi-head attention allows the model to jointly attend the information of different representation subspaces at different positions, with a single attention head averaging inhibits this. Okay, so again, they're talking about how really what they've done is they've created a mechanism for attention that is just better at parallelism, which is a big deal in machine learning. So, they have some math here. Where the projections are parameter matrices, this math. In this work, we employ h equals 8 parallel attention layers or heads. For each of these, we use these. Due to the reduced dimension in each head, the total computational cost is similar to that of single head attention with full dimensionality. So they're saying it's not much more efficient, but it's better. Applications of attention in our model. The transformer uses multi-head attention in 3 different ways. In the encoder-decoder attention layers, the queries come from the previous decoder layer and the memory keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions of the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models, such as in these examples. So this part's really important. What they're saying here is they have taken out a human step, right? Because in these old models, in these examples that they have listed, it would have been a human or, some kind of script or something reviewing the output of the model to decide whether or not it was good, which is something that we still do, but with multi-headed attention, we do it less frequently, right? We're getting more completed outcomes because we have a more sure mechanism providing us its next best guess. So the encoder contains self-attention layers. In self-attention layer, all of the keys, values, and queries come from the same place. In this case, the output of the previous layer in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Similarly, the self-attention layer in the decoder allows each position in the decoder to attend to all positions of the decoder up to and including that position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside of a scale dot product attention by masking out or setting to negative infinity all values of the input in the softmax, which correspond to illegal connections, see figure 2. So what they're saying here is it's really important that every single layer in the model knows about everything above it and everything below it. That gets us into position-wise feed-forward networks. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. This consists of 2 linear transformations with a ReLU activation in between. Here's some math. With the linear transformations are the same across different positions, they use different parameters from layer to layer. Another way of describing this is as 2 convolutions with kernel size 1. The dimensionality in input is D model equals 512, and the inner layer has dimensionality of 2048. Similarly to other sequence transduction models, we used learned embeddings to convert the input tokens to output tokens to vectors of dimension D model. We also used the usual learned linear transformation and softmax function to convert the decoder output to the predicted next token probabilities. In our model, we share the same weight matrix between the 2 embedding layers in the pre-softmax linear transformation, similar to this example. In the embedding layers, we multiply those weights by the square root of D model. Here they're just showing more math. I'm not going to get into the math because I'm not an expert on it, but as I learn more, maybe I can revisit this paper and talk more about the math. We'll see. Next, they talk about positional encoding. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some sort of information about the relative or absolute position of the tokens in the sequence. To this end, we add positional encodings to the input embeddings at the bottom of the encoder and decoder stacks. This positional encodings have the same dimensions of the model as the embeddings, so the two can be summed. There are many choices of positional encodings, learned and fixed. In this work, we used sine and cosine functions of different frequencies. Here's some math. Where the pos is the position I and the dimensions, that is the dimension of the positional encoding, corresponds to a sinusoid. The wavelengths from a geometric progression from 2 pi to 10,000 times 2 pi, we chose, or I say times, but that may not actually be the operation here. We chose this function because we hypothesized it would allow the model to easily learn to attend by relative positions, since for any fixed offset of this can be represented as a linear function of that. We also experimented with using learned positional embeddings and instead found the two versions produce nearly identical results. And we chose the sinusoidal version because it may allow the model to extrapolate the sequence lengths longer than the other ones encountered during training. So what they're saying here is there's more work to be done to find the perfect transformer. Why self-attention? In this section, we compare the various aspects of self-attention layers to the recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representations to another sequence of equal length. Such as a hidden layer in a typical sequence, transduction encoder or decoder. Motivating our use of self-attention, we considered 3 desiderata. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized, as measured by the minimum number of sequential operations required. The third is the path length between the long-range dependencies in the network. Learning the long-range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependencies is the length of the paths forward and backward signals have to traverse in the network. The shorter these paths between any combination of positions in the input and the output sequences, the easier it is to learn long-range dependencies. Hence, we also compare the maximum path length between any two input and output positions in networks composed of the different layer types. As noted in the table, a self-attention layer connects all the positions with a constant number of sequentially executed operations, whereas a recurrent layer requires sequential operations. In terms of the, or O to the N, in terms of the computational complexity, self-attention layers are faster than recurrent layers when the sequence length N is smaller than the representation dimensionality D, which is most often the case with sentence representations used by the state-of-the-art models in machine translations, such as the word piece and byte pair representations to improve computational performance for tasks involving very long sequences. Self-attention could be restricted to considering only a neighborhood of size R in the input sequence centered around the respective output position. This would increase the maximum path length to O to the N to the R. We plan to investigate this approach further in future work. A single convolutional layer with kernel width 1 or less than N does not connect all pairs of inputs and output positions. Doing so requires a stack of convolutional layers in the case of contiguous kernels, or a log function in the case of dilated convolutions. Increasing the length of the longest paths between any two positions of the network, convolutional layers are generally more expensive than recurrent layers by a factor of k. Separable convolutions, however, decrease the complexity considerably. The complexity of separable convolution is equal to the combination of self-attention layer and pointwise feed forward layer, the approach we take in our model. As a side benefit, self-attention could yield more interpretable models. We inspect attention distributions from our models and present and discuss examples in the appendix. Not only do individual attention heads clearly learn to perform different tasks, many appear to exhibit behavior related to the syntactic and semantic structure of the sentences. We trained on the standard English to German data set about 4.5 million sentence pairs. Sentences were encoded using the byte pair encoding, which has shared source target vocabulary of 37,000 tokens. For English French, we used the significantly larger WMT, English to French, 36 million sentences. Sentence pairs were batched together by approximate sentence length. Each training batch contained a set of sentence pairs containing approximately 250,000 source tokens and 250,000 target tokens. Hardware and schedule. We trained our models on a machine with 8 NVIDIA P100 GPUs. This is crazy. This is such a small amount of hardware for how important this paper is. For our base models, using the hyperparameters described throughout the paper, each training step took about 0.4 seconds. We trained the base models for a total of 100,000 steps or 12 hours. For our big models, described on the bottom of the table, the step time was 1 second, and the models were trained for 300,000 steps, which is about 3.5 days. We used the Atom Optimizer with these settings. We varied the learning rate over the course of training according to the formula this. This corresponds to increasing the learning rate linearly for the first warm-up steps training step and decreasing it thereafter proportionally to the inverse square root of the step number. We used warm-up steps equals 4,000. So what they're saying is skew your knowledge of stuff more towards the beginning of what is happening, and then we'll take away how interested you are in those metrics as we get further on in training, just so that they can get a good understanding of the data set without overfitting, I think probably was their goal here. We employ 3 types of regularization during training. Here they are. Residual dropout. We apply a dropout to the output of each sublayer before it is added to the sublayer input and normalized. In addition, we apply the dropout to the sums of the embeddings and the positional encodings in both the encoder and decoder stacks. For the base model, we use a rate of this. Label smoothing. During training, we employed a label smoothing value of this. This hurts perplexity as the model continues to be more unsure, but improves accuracy and the score we were measuring. And the results. So on the English to German, we already talked about these results. Our base model in different ways, measuring the change in performance on the English to German translation on the variations of transformer architecture. Unlisted values are identical to those of the base model. All metrics on the English to German translation set listed perplexities per word piece according to our byte pair encoding and should not be compared to per word perplexities. To evaluate if the transformer can generalize to other tasks, we performed experiments on English constituency parsing. This task presets specific challenges. The output is subject to strong structural constraints and is significantly longer than the input. Furthermore, recurrent neural network sequence-to-sequence models have not been able to attain state-of-the-art results in small data regimes. We trained a 4-layer transformer with D model equals 1024 on the Wall Street Journal portion of the Penn Tree Bank, about 40K training sentences. We also trained it in a semi-supervised setting using the larger high-confidence Berkeley parser Corpora, from which approximately 17 million sentences. We used a vocabulary of 16,000 tokens for the WSJ and the setting of vocabulary 32K tokens for the semi-supervised setting. We performed only a small number of experiments to select the dropout, both attention and residual, learning rates and beam size, and development set, and all other parameters remained unchanged from the English to German translation model. During inference, we increased the maximum output length to input length plus 300. We used a beam size of 21 and A equals 0.3 for WSJ only and the semi-supervised setting. Our results in Table 4 show that despite the lack of task-specific tuning, our model performs surprisingly well, yielding better results than all previously reported models with the exception of the recurrent neural network grammar. In contrast to RNN sequence-to-sequence models, the transformer outperforms the Berkeley parser even when training only on the WSJ training set of 40K sentences. That's huge. What they're saying is, we trained our thing on 40,000 sentences from WSJ, and it was better in the area of measurement for even the Berkeley parser, which I'm not sure the history of, but they made something better. In conclusion, in this work, we presented the transformer, the first sequence transduction model based entirely off of attention, replacing the recurrent layers most commonly used in encoder-decoder architecture with multi-self-head attention. For translation tasks, the transformer can be trained significantly faster than the architectures based on RNNs or CNNs. For these two data sets, we achieved new state-of-the-art. In the former task, our best model outperforms even all previously reported ensembles. We are excited about the future of attention models and plan to apply them to other tasks. We plan to extend the transformer to problems involving input and output modalities other than text to investigate local restricted attention mechanisms to efficiently handle large inputs and outputs such as images, audio, and video. Making generation less sequential is another research goal of ours. The code we use to train and evaluate our models is available here. Acknowledgements. We are grateful to these people, and here are our references, and references there are many. Here's an example of the attention mechanism, and this is where we'll leave it off, right? So this is a visualization of an interaction happening in between two layers of the generative pre-trained transformer, right? And it is connecting all of these words to this word, right? And it's trying to figure out, okay, so it has a neuron that is connected to making and to 2009, and to making and to more. If it's making, it thinks it's making more, making difficult. It has strong correlations with these words. I believe this EOS is kind of, some kind of mechanism for saying, I'm not sure what to do. And it's just interesting to see like the strength of the correlation with the color, right? So like the deeper gray lines are not as confident, and this one that's almost white is very confident. So it thinks it's going to make a connection between making and difficult. And this is probably the decision that it made and passed forward as the next stem of the next word. So closing thoughts here. My main takeaway the first time I read this paper was that they have been really clever about what they decided to target here, and at the same time they introduced concurrency, which is something that any programmers in the audience will already know has like these kinds of like 10x benefits of making things way faster. And I think they just merged those two things here. A good idea about reducing human interaction with machine learning models, and simultaneously adding programmatic concurrency. And that just changed the game for neural networks. This article was published in 2017, and obviously shit has gotten weird since then. But yeah, I just wanted to read through this paper with y'all, just so I'd have something to post today. Don't forget to give the video a like if you made it this far, and subscribe to the channel if you're new and you want to see more security, machine learning, or other versions of content. That's it. See ya. Thank you. Bye-bye.